Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3d hybridization with two lone pairs in the main structure. For this case, I'm taking the example of bromine trifluoride. So our today's example is bromine trifluoride. That's BrF3. Now let's make the Lewis structure of BrF3 first. That's our bromine over here. That's fluorine, fluorine, and the fluorine. Now let's talk about bromine first. First of all, the bromine is the member of group number 17, that's halogens. And we all know that halogens have 7 electrons in their valence shell. Now let's mark the 7 electrons around the bromine in the Lewis structure. That's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, and the seventh electron. Now let's talk about the fluorine. Fluorine is also the member of group number 17. Its atomic number is 9. So its configuration is obviously 2, 7. That means fluorine is also going to have 7 electrons in its valence shell. Now let's mark the 7 electrons around all the fluorine atoms. So let's talk about first fluorine atom. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the second fluorine. The first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, and the seventh electron. Now let's come to the third fluorine. The first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, and the seventh electron. So now let's make the covalent bonds. Now here in this case, all the fluorine atoms are going to make 1-1 bond with the bromine. So that's the first covalent bond of first fluorine with the bromine. Now it's the turn for the second covalent bond of second fluorine with bromine. Now that's the third covalent bond with the bromine. Now let's count the number of valence electron for fluorine after the formation of 1-1 bond with bromine. Now I'm counting the number of valence electron for the first fluorine. That's the first electron, second electron, third electron, fourth electron, fifth, sixth, seventh, and the eighth. So the first fluorine has attained octet, that is 8 electron in its valence shell after the formation of 1 bond with bromine. Now let's count the number of valence electron for the second fluorine after the formation of 1 bond. So that's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh electron, and the eighth electron. So the second fluorine has also attained octet, that is 8 electron in its valence shell after the formation of 1 bond with bromine. Now let's count the number of valence electron of the third fluorine also. That's the 1 electron, second electron, third, fourth, fifth, sixth, seventh, and finally the eighth. So the third fluorine has also attained octet, that is 8 electron in its valence shell after the formation of 1 bond with bromine. Now let's count the number of valence electron for bromine after the formation of 3 bonds with 3 fluorine. So now that's the first electron, second electron, third electron, fourth electron, fifth, sixth, seventh, eighth, ninth, 10th. So here bromine has attained 10 electron in its valence shell after the formation of 1-1 bond with bromine. Why bromine is eligible for the expansion of octet? Because bromine is having vacant d orbital in its valence shell. Now let's talk about the hybridization now. Now let's come to the bromine first. That's our bromine. We all know that bromine is the member of group number 17. What's the group number 17? That's fluorine, chlorine, bromine, iodine. The group number 17 has a general electronic configuration of ns2 np5, where n is the period number. Now, fluorine belongs to the second period, chlorine to the third period, and bromine to the fourth period. So the configuration of bromine comes out to be 4s2 4p5, and it's also having the d orbitals, so it's 4d0. So we got the electronic configuration of bromine to be 4s2 4p5 4d0. Now let's make the orbital diagram in the form of boxes for the bromine. It's 4s2 4p5 4d0. Now we know that s subshell has only one orbital, so I have made one box or the one orbital for the 4s. In case of p subshell, we know that p subshell has 3 degenerate orbitals, so we have made 3 orbitals or the 3 boxes for the 4p, and in case of 4d we have 5 degenerate orbitals. What do we mean by degenerate orbitals? The orbitals which are having equal energies. So that's the 4d. Now let's fill the electrons according to the electronic configuration. Now the 4s is having 2 electrons. Let's fill the 2 electrons in the orbital of 4s. That's the first electron with a spin of plus 1 by 2, and that's the second electron with a spin of minus 1 by 2. Now 4p is having 5 electrons. Let's fill that 5 electrons according to the Hounds rule, and Hounds rule states that in case of degenerate orbitals, firstly all the orbitals will get 1 electron each. After that, pairing will start. So that means that's our first electron in the first orbital, second electron in the second degenerate orbital, and the third electron in the third degenerate orbitals. So now here the Hounds rule has obeyed. Now we have to start the pairing of electron from the fourth electron of 4p. So that's the fourth electron in the first orbital with a spin of minus 1 by 2, and lastly we have the fifth electron in the second orbital of the 4p with a spin of minus 1 by 2. So that's the electronic configuration of bromine, and that's our ground state. Now let's come to the Lewis structure. In Lewis structure, we can easily observe that bromine is forming 3 covalent bonds. The bromine is forming 3 covalent bonds. As all the bonds are single bonds, so that's why they all will be sigma bonds. So here bromine is forming 3 sigma bonds. And for the formation of 3 sigma bonds, the bromine must have 3 atomic orbitals containing 1 electron each, so that 3 orbitals of bromine containing 1 electron can overlap with the orbitals of fluorine for the formation of 3 sigma bonds. So what we are going to do now, here the 1 electron from the 4p will get excited from 4p orbital to the 4d orbital. By this way we can have the 3 unpaired electrons in the 3 different atomic orbitals for the formation of 3 sigma bonds. So now let's make that. That's our 4s. These are the 3 degenerate orbitals of 4p, and these are the 5 degenerate orbitals of 4d. Now the 4s is having 2 electrons. The 4p is now having total of 4 electrons, as one of the electron from 4p orbital has been excited to the 4d orbital. So now 4d is having 1 electron, and by this way we got the 3 orbitals containing 1 electron each for the formation of 3 sigma bonds, and this is called the excited state. That's called the excited state. Now from this portion, as all the bonds are sigma, so from this point I'm taking the step of intermixing of atomic orbitals, that's hybridization. So here intermixing of atomic orbitals will start from the s orbital of the valence shell, and orbitals having the electrons will be involved in the hybridization process, and the atomic orbitals which are containing 1 electron, then only that atomic orbitals will be involved which will form the sigma bonds only, but not the pi bonds. Here the atomic orbitals containing 1 electron each will get involved in the hybridization process, only that which can form the sigma bonds but not the pi bonds. So here 1 s orbital, 3 p orbitals and 1 d orbital. 1 d orbital will intermix. Now this intermixing process of atomic orbitals is called hybridization. Now here total of 5 atomic orbitals are mixing, that is 1s, 3p and 1d. So we will get the 5 new hybrid orbitals of equal energies. We are going to have 5 new hybrid orbitals and they all are degenerate, that is of equal energies. So I am writing come degenerate orbitals. So in intermixing process, the atomic orbitals containing electrons and the atomic orbitals which are containing 1 electron will be involved, and the atomic orbitals containing 1 electron will form the sigma bonds in case of hybridization. So we got the 5 new hybrid orbitals come degenerate orbitals. I am marking the 5 hybrid orbitals now. I am saying it again, in the hybridization process, the atomic orbitals which can form sigma bonds will be involved, but not the pi bonds. So here all were the sigma bonds. So this is not the case of pi bonds. We will do that in the next lectures. So here we got the 5 new hybrid orbitals, and the name of hybrid orbitals will be, here is the involvement of 1s, 3p and 1d. So the hybrid orbital will be named as sp3d hybrid orbital. The second orbital is also sp3d hybrid orbital. Third one is also sp3d hybrid orbital. Fourth one is also sp3d hybrid orbital, and the fifth one is also sp3d hybrid orbitals, which is having 20% s character plus 60% p character and 20% d character per hybrid orbital. And in hybridization process, the orbitals which are mixing will form only sigma bonds but not the pi bonds. Here in the Lewis structure we got the 3 sigma bonds. So we have intermixed the orbitals which are having electrons plus the orbitals which are having 1 electron plus, and that orbital which are having 1 electron will form only sigma bonds, not the pi bonds. So here in total we are having the 2 electrons in 4s, 4 electrons in 4p and 1 electron in 4d. So in total we are having 7 electrons. So now let's fill that 7 electrons in sp3d hybrid orbitals according to the Hounds rule. So that's the first electron, second, third, fourth, fifth, sixth and the 7th. So we got the 7 electrons in the 5 sp3d hybrid orbitals. Now, here we are having two hybrid orbitals which are having two electrons. So first sp3d hybrid orbital is having 2 electrons. The 2 electrons in hybrid orbitals is termed as lone pair of electrons. So that's the lone pair of electrons. Now the second sp3d hybrid orbital is also having 2 electrons. So again these 2 electrons of sp3d hybrid orbitals will be considered as the lone pair of electrons. Now let's come to the Lewis structure. In Lewis structure we are having 2 lone pair of electrons. So these are the 2 lone pair of electrons. Now let's come back to hybridization. Here now let's talk about the fluorine atom. Fluorine, the atomic number is 9. So the configuration will be 2s2 2p5. Now let's make the 2p orbitals. We are having 3 orbitals in 2p and these all 3 are degenerate. Here we have to fill 5 electrons in 2p. The first electron, second, third, fourth and the fifth. So in fluorine we are left with one atomic orbital in 2p which is having one electron, and that atomic orbital is going to overlap with the hybrid orbital of bromine for the formation of sigma bond. Now let's make it. Here I am marking that's the 2p of first fluorine, 2p of first fluorine atom, and we are having 5 electrons. So that's first, second, third, fourth and the fifth. So the atomic orbital which is having one electron will have head-on overlap with the sp3d hybrid orbital of bromine for the formation of sigma bond. So we got the sigma bond, sigma sp3d p. Why so? Because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of bromine with the p orbital of fluorine. Now let's talk about the second fluorine atom. That's the 2p of second fluorine, and we are having 5 electrons in 2p. So that's the first electron, second electron, third electron, fourth electron, fifth electron. Now here we are having one atomic orbital which is having one electron, which is going to have head-on overlap with the sp3d hybrid orbital of bromine for the formation of sigma bond. So we got the sigma bond again, that sigma sp3dp, which has been formed by head-on overlap of sp3d hybrid orbital of bromine with the p orbital of fluorine. Now let's talk about the third fluorine atom. This is the 2p of third fluorine. That's the 2p of third fluorine atom. Again 2p is having 5 electrons. That's the first electron, second, third, fourth and the fifth. Here also we have left with one atomic orbital which is having one electron, which is going to have head-on overlap with the sp3d hybrid orbital of bromine for the formation of sigma bond. So we got the sigma bond, sigma sp3d p, because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of bromine with the p orbital of fluorine. So now let's talk about the structure. In structure we are having 2 lone pairs. So now let's mark them in the main structure. First of all, we got the hybridization to be sp3d. What's the standard structure of sp3d hybridization? That's trigonal bipyramidal. That's trigonal bipyramidal. Let's make it. That's our bromine. That's the fluorine atom forming the sigma bond. Here we are having one lone pair of electron, and here we are also having another lone pair of electron, and these two lone pair will occupy the equatorial position in the structure. So, and this is just an imaginary linkage which I'm making with the dotted lines to make you clear this structure in 3 dimensions. So we got the 2 lone pairs on the equatorial position. Now we are left with 2 fluorine atoms. That's the second fluorine atom of the main structure, and that's the third fluorine atom of the main structure. So now while naming the structure, we have to ignore the lone pairs. After that, after ignoring the lone pairs, this structure will be of shape called T sorry, of name called T shape. We are not going to name it as trigonal bipyramidal. The structure of BRF3 containing 2 lone pairs in the main structure with the hybridization of sp3d will be named as T shape. So here the name of BRF3 geometry in sp3d hybridization with 2 lone pairs on the equatorial position is named as T-shape structure. So this is the T-shape structure. So now at last, let's talk about the energy points. Here we are having 2 endothermic processes. The first one is consumption of energy for the promotion of electron from 4p to 4d. So I am writing here is the consumption of promotional energy. Here is the consumption of promotional energy. After that, the another endothermic process is the intermixing of atomic orbitals. So that's called hybridization process, and that energy will be called as hybridization energy. So here is the consumption of hybridization energy. That's the consumption of hybridization energy. Now at last, there is a exothermic process, that is the formation of 3 sigma bonds. So I am writing here, comma, energy is released during the formation of 3 sigma bonds between hybrid orbitals of bromine and p orbitals of fluorine. Now the energy which is released compensates the promotional energy, which compensates promotional energy, and hybridization energy, as both of the endothermic energies, that's the promotional energy and the hybridization energy, is compensated during the formation of 3 sigma bonds between the hybrid orbitals of bromine and the p orbitals of fluorine. That's the reason the BRF3, the formation of BRF3 is chemically feasible or practically possible. So that's all about the hybridization of BRF3, that's sp3d with 2 lone pairs in the structure. And whenever sp3d hybridization is having 2 lone pairs, we always place that 2 lone pairs on the equatorial position, and that structure is named as T shape, not the trigonal bipyramidal. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on the thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.